Okay, so in our third radioactivity video, we are going to look at some of the properties of radiation. We're going to look at some of the ways it can harm us and how we protect ourselves from it. And we are also going to look at the concept of half-life and how we study the rate of decay of radioisotopes. So let's start by talking a little about the properties of radiation or radioactive emissions. So all alpha, beta and gamma can all produce ionizations in materials which they pass through. And by ionizations, we mean they can basically knock electrons out, they can break chemical bonds, they can break the bonds, for example, in your DNA, which might cause a mutation, which then might lead to uncontrolled growth, which might be a cancer, for example. So in a sense, that's why they're dangerous. They can basically break the bonds in living things and stop them from living normally, in a very simplified sense. Apologies to the biologists. Now, firstly, let's talk about the penetrate. I tried to use the term penetrating power. In here, they just use the term penetration of the various types of emissions. And obviously, alpha particles are very big. They're very easily stopped. They'll only travel about 2 to 3 centimetres through air. They can be stopped by something like a sheet of paper. So because of their large size, they can't really push through other atoms. Beta particles can travel about 1 metre through air, but they're stopped by about a 1 mil thick piece of aluminium. So because they have a charge, they will interact quite strongly with the atoms that make up a material, which is also made of charged particles, so they don't tend to travel very far through solid matter. Gamma radiation, on the other hand, has no charge, has no mass, can go from almost unlimited range in air, and you'd need about 20 centimetres of lead to effectively stop most of the gamma radiation. So basically, the gamma is much harder to stop. Doesn't talk about it here, but I would have talked about it in year 11 with those students I had. The alpha ones, though, because they're big in charge, they do the most damage to you. So they have the greatest ionizing ability, the greatest ability to harm what they hit. Beta are sort of in the middle, and gamma are actually not that likely to cause ionizations because they don't have a charge or a mass, so they're less likely to interact with the atoms they come across. They still can, but they're less likely. Now, the other thing we need to talk about, and I should have left room for a diagram for this, is how we use electric and magnetic fields to determine or to detect alpha and beta and gamma particles, or detect and identify them. And so yeah, this should be a good little bit of revision from earlier in the year. So let's think, use this space up the top here. If we have, say, an electric field, so we say have 2 plates, positive and a negative. If we put a beta plus particle through there, positive charge, so that'll get bent downwards. If we put a beta minus particle through there, negative charge will get attracted to the positive, so that'll get bent up. If we put an alpha particle through there, that actually has 2 protons, 2 neutrons, no electrons, so it's basically got a 2 positive charge. So just like the beta plus particle, that gets bent downwards. And if we put a gamma through there, that has no charge, so that will just travel straight through. Now, we can also think about with this what happens if we fire them into a magnetic field. Because we know that a charged particle will affect things travelling through a magnetic field. And so we use our right hand palm rule. So a positive charge in this case, so fingers into the page, thumb in the direction of a positive charge. So the positive charge, say, of our beta plus particle will get bent upwards. If we have an alpha particle, once again, that will get bent up. Now, in this case, its mass is much, much greater. So if we use our R equals mv on QB formula, that tells us that if the mass is much greater, the radius will be bigger. The charge is actually bigger also, but the charge is only double that, whereas the mass is about 4,000, or no, it's actually even more than that. It's much, much bigger. So that will get bent up, but with a much bigger radius. That's not drawn to scale there. With our gamma, again, no charge, so that will travel straight through the field. And I haven't really left much room here for my beta minus, but I think you get the idea. That will travel the opposite direction to a positive, so that will get bent down. Sorry for drawing over the notes there, but I don't think that will matter too much. So that's how we use electric and magnetic fields. Good little bit of revision to identify alpha, beta plus, beta minus, and gamma radiation. Let's now talk about the effects of ionizing radiation on living matter. So, in addition to alpha, beta, and gamma, other radiations, including X-rays, neutrons, protons, cause ionization in matter. They are collectively called ionizing radiation. So, in the same way as alpha, beta, and gamma can damage you, X-rays, neutrons, and protons also have a similar effect. So, as we talked about before, ionizing radiation can break chemical bonds in living matter, and this can kill the cells. So, in a sense, that's like a radiation burn, in the same way as sunburn is being burnt by UV radiation. Well, this radiation is even much, much more higher energy and can burn you in a similar way, or even in a worse way, if you get exposed to high levels of radiation, say in a nuclear power plant disaster or when a nuclear bomb explodes. Longer term exposure to lower levels of radiation can also damage your genetic material, so your DNA. That can mean your cells can't replicate properly, and that can lead to things like uncontrolled growth in cells, which can lead to tumours and cancer. So, how can we protect ourselves from radiation? Well, in essence, 3 ways we can do that. We can increase the distance from the source, stand further away. We can limit the time of exposure, so don't stand there for too long near a radiation source, or we can use shielding. So an example there is an X-ray technician might wear a lead apron to stop or minimise their exposure to harmful X-rays. Okay, let's talk about the mathematics of radioactive decay, and particularly the concept of half-life. I don't want to spend a lot of time on this. If you've done year 11 with me, you would have done a lot of this and we would have covered this. If you're doing mathematics in other subjects, you will be doing a lot more complex and difficult stuff on exponential decay, so I don't think you'll find that challenging. And even if you do find this a little bit confusing to start, when I go through a problem in the next slide, I think you'll realise it isn't actually that difficult. So let's just go through what we have here. So the number of radioactive nuclei in a sample of a given isotope decrease exponentially with time. So if we look at the number of atoms in a decaying sample, we get this sort of exponential decay shaped curve. Now the half-life is the time required for half of the radioactive nuclei in the sample to decay. So the half-life is the time to go from 100 to 50, or 50 to 25, or 25 to 12.5. So 1 half-life, 2 half-life, 3 half-lives. Radioactive decay is a random process with a constant probability and hence a constant half-life. So, we'll come back to, I think, that in a second. Half-life is independent of both physical state and chemical state. So it doesn't matter what temperature the isotope's at, it doesn't matter what other atoms the radioactive nuclei is bonded to, that half-life will not change. So the activity of a radioactive sample, of a radioactive substance, is the number of radioactive nuclei that decay per unit time. So we can either measure the number of atoms, as we talked about up here, or we can look at what we call the count rate, or the number of decays, or the activity of a radioactive sample. Now, activity is proportional to the number of radioactive nuclei present, and hence also decreases exponentially with time. So, the number of, because of this point up here about a constant probability of decay that I said I'd come back to, the more atoms you have, the more decays you get. So you'll get twice as many decays if you've got 100 atoms as you would 50. Therefore, the number of atoms is proportional to the count rate, or the number of decays, or the activity. For a given nucleus, the half-life for the activity is the same as the half-life for the number of radioactive nuclei. So what I've just said, the time to go from half, the number of atoms will be the same for the activity to go for half. The other thing we need to know is that the activity of a radioactive sample is the number of decays per second. The unit of activity is the becquerel. 1 becquerel is equal to 1 decay per second. Now, you might be a little bit confused at the moment. Let's go and look at a problem, and hopefully this will seem clearer. Okay, we've got a previous exam question here. So I haven't picked an easy question. I've tried to pick a representative question. So it's talking about the half-life of fluorine-18 is 110 minutes. The activity of a sample of fluorine-18 was measured at 12:30 and found to be 1.2 times 10 to the 7 becquerel. Determine the activity that you would expect the sample to have at 6 p.m. the same day. So let's look at how we solve this problem. You could solve this mathematically, if you like, with a formula. I'm not even going to show you that because I don't want to confuse the people who haven't done that mathematically. If you know how to do that, then I'm sure you'll be able to work that out. If not, this sort of method I think will serve you well as well. So let's do the usual, write down the information in the question. So the half-life is equal to 110 minutes. The activity of the sample was initially 1.2 times 10 to the 7 becquerels. And we've got to work out the time between 12:30 p.m. and 6 p.m, which is equal to 5.5 hours, which is equal to 330 minutes, 60 minutes in an hour. So this is the way I would approach that. Let's think about the number of half-lives. So we start off at time 0, 1 half-life, 2. I think you can probably guess that we won't need to go past 3 half-lives. So let's think about that in time. 0, 1 half-life is 110 minutes. 2 will be 220 minutes. 3 half-lives will be 330 minutes. So what would the activity be? Well, initially it is 1.2 times 10 to the 7. That will half after 110 minutes. So it'll be 0.6 times 10 to the 7. We would usually write that, though, as 6.0 times 10 to the 6. Hopefully you've gotten a good enough understanding of exponential notation to see that. After 2 half-lives, it will have dropped to half again. So 3 times 10 to the 6. After another half-life, it will be 1.5. So half again times 10 to the 6 becquerels. So that is our answer.